Welcome to Math 31. This is a lesson on the derivatives of sine and cosine functions. So at last we're going to start differentiating trigonometric functions. Let's start by reviewing the basic idea behind the derivative using first principles. So any function y equal f at x, the derivative is going to be the limit of f at x plus h minus f at x over h as h approaches 0. So this will bring you back to the earliest times of our differentiation. So this should apply when you're dealing or looking for the derivative of a trigonometric function. So if you did want to get the derivative of sine x with respect to x, this step should make sense. And then when we take a look at sine x plus h, and then if you use the sum difference formula sine a plus b, then you'll get something like this. Now I'll just write the limit part of it. The limit as h approaches 0 of, you've got the formula in front of you, so I won't write it out again, but it's the sine of x times the cosine of h plus the cosine of x times the sine of h, and then minus the sine of x. All over top of h. Now on its own, this doesn't really do much for us. We don't see any sort of common factor that can be removed because there is none. But if we rewrite this one, we'll get the limit as h approaches 0. Take this term and this term because they both got sine x in them. So sine x cos h minus sine x, and then plus cos x sine h all over top of h. And now if you take a look at these first two terms and go further with this by splitting up the fraction a little bit, you could write this as sine x cos h minus sine x all over top of h, and then plus cos x sine h over top of h. I'll bring up a new screen to get some space, but you're probably thinking the same thing I am. First off, this is one big limit. We could split this into two, which I will do when I go through the rest of this. But we also can take out a factor of sine x from that expression, at least the first cluster. So that would turn into the limit as h approaches 0 of sine x, and then factored out we have cos h minus 1 over h, plus then we had cos x sine h over h. So when we do take the limit, replace h with 0 if we can, we'll get sine x. There is no h variable. Now normally we'd be shut down at cos h minus 1 over h. However, looking at what we know about limits, that's actually equal to 0. So we have the form for that. And then the second part, cos x will stay as is, but the sine h over h is 1. So that tells us then that the derivative of sine x is actually equal to cos x. Meaning that if you ever need to find the slope of the tangent line at any point on that sine curve, what you do is you take the cosine of that value, and then that gives you the slope of the tangent line. We'll use that later on with some sort of applications and graph questions. Now, the other thing is that the same method is used to find the derivative of cosine. To differentiate y is equal to cosine x. And if you did this, you would see the derivative of cosine x is equal to negative sine x. So this is true, and it warrants a box around it. This is true. It also warrants a box around it. Both of these are available on your formula sheet, so you don't have to memorize them. You probably will, though, because you'll work with them an awful lot. Now, the next thing is that this is only defined as the derivative of x. And more often than not, you're going to be differentiating a more complex function. So in those cases, we use the chain rule. So if you're given any function u is equal to f of x, we want to determine these two derivatives. So with the chain rule, we would simply get that the derivative of sine u is equal to cosine u, and then multiplied by the derivative of the inner. So that's classic chain rule. And the same thing would work with the derivative of cos u. The derivative would be equal to negative sine u multiplied by the derivative of whatever the inner function was. Now, having this information, let's differentiate a number of these problems and see if we can get comfortable with it. So number one, y is equal to the sine of 8x. Now, I'm going to be fairly conservative with these. One of the problems that most people run into when they're differentiating trig functions is they get kind of lost with all the trig functions. They don't really flow as well as a polynomial. And as you've seen, what really you're doing when you're differentiating these is you're just going from sine to cos or cos to sine. So it's very difficult to figure out which stage of the differentiation you're at. So you really have to be careful when you're working these ones out. You don't expect your answers to make any sort of sense. You just have to trust that you're doing it well, doing it properly. So dy dx is equal to the derivative of sine 8x, which is cosine 8x, multiplied by the derivative of the inner, so d dx 8x. Do not forget that part. And then dy dx is equal to cosine of 8x times 8. Now that 8 is not part of the argument. It's not within the cosine function. It's being multiplied to it. So it's actually equal to 8 cos 8x. And that's how it works. Now the second one, pretty much the same thing, except we've got two terms being subtracted. So the derivative of this is equal to 4. Well, 4 times the derivative of sine. The derivative of sine is cosine 2x. But don't forget you have to multiply by the derivative of 2x with respect to x. And then moving on, this is minus 3 times the derivative of cos 5x. The derivative of cos is negative sine 5x. So note how cos turns into negative sine. Then multiplied by the derivative of 5x. Now I'm not going to get too carried away with this. I'm going to now go to the stage where the derivative of 2x is 2. 2 times 4 in front is 8 cos 2x. And then minus a minus, of course, is plus. And then 3 times 5 is 15 sine 5x. And there we have it. Works out nicely, but you need to be careful. Now the next question illustrates a very common problem with trig functions. These two. One is the cos of x cubed, and one is the cos of x cubed. And you've got to be able to make the distinction between those two. Now it all has to do with the location of the exponent. This function really is the cosine of x all cubed. So if you were to differentiate it, you would use the chain rule first, seen as the entire function is being cubed. So that would be 3 times the cosine of x squared. I'm using brackets with these a lot because that's really important for organizing and keeping one term separate from the other. So 3 times cos x squared times the derivative of cos x. So the derivative of cos x is negative sine x. And now we put the whole thing together. dy dx is equal to 3, negative 3, because we have that negative in front. And then we have cos squared x. So I'll put the exponent back where it belongs because I'm done with it. And then multiplied by the sine of x. Now that's a very different thing than this one, because in this case it's only the x that's being cubed. So dy dx is equal to the derivative of cos x cubed is negative sine x cubed, but we're multiplying by the derivative of x cubed with respect to x, which is 3x squared. So dy dx is equal to negative sine x cubed times 3x squared. Now keep in mind that is being multiplied, so this would in fact be negative 3x squared sine x cubed. So those are two very, very different expressions. So the rest of these ones, nothing really new happening. We just got to be careful with them. I would advise you to write this one with brackets where we want them to be. So this is the sine of 3x, and then I'm using a square bracket around it to the 2. I want it to be clear that that 2 is the exponent for the entire function. So that when I differentiate now dy dx, this is going to be equal to 2 times the sine of 3x to the 1, if you want it there, multiplied by the derivative of sine 3x. Now I like to work down with these ones and then put it all together. The derivative of sine 3x is cosine 3x. And then this has to now be multiplied by the derivative of 3x. Now this is overkill. Most of you would do these last two steps together, and that's fine. I'm making this one go about as slowly as I can. But you've got to be thinking those things. So this is 2 multiplied by the sine of 3x multiplied by the cosine of 3x. And all this is being multiplied by 3. So dy dx is equal to 6 sine 3x times cos of 3x. Now this is correct. However, there is an optional way to express the answer, which you see an awful lot. And it's a little more compact, so people kind of like it like that. So whether you recognize it or not, this is actually of form sine 2a is equal to 2 sine a cos a. And that is true if you take a look at it at this point right there. I even put a bracket around it. So if you let the a value, if you recognize that a is equal to 3x, then this expression there, a lot of arrows going around here, is going to be 2 sine a cos a, all multiplied by 3. And then that's going to be simplified to sine 2a, all multiplied by 3. So in fact, since a is 3x, this is the sine of 2 times 3x times 3. So this is sine 6x. And let's put that 3 out in front where you would normally see it. So this is a convenient way to write it, a little more compact. Now, if this was an open-ended question, you wouldn't be required to do it, but it also gives a little bit more information, and it may or may not be easier to solve if it got right down to that. Setting it to 0, finding out where the graph is having a turning point or whatever. Next one, pretty routine, except we have a radical. So y is equal to 1 minus 3 sine 2x to the 1 half. Feel free to pause me and go through this one on your own. Now dy dx, when you differentiate this, is 1 half times 1 minus 3 sine 2x to the negative 1 half, multiplied by the derivative of the inner, which is 1 minus 3 sine 2x. And then when we do differentiate that inner, we'll get negative 3, well, the derivative of sine 2x is cos 2x, and then times the derivative of 2x. Now, I'm getting tired of writing this d dx all the time, so soon I'm going to stop doing that, because in fact, by writing all these steps, you're making a sort of a notation error very possible. So this is 2, and we get negative 3 times cosine of 2x, all times 2, and then the first stage of the differentiation was 1 half times 1 minus 3 sine 2x to the negative 1 half. And then when we mop this one up, we'll see that 1 half is going to cancel with the 2 over there. So we also all we have left is a negative 3 cosine 2x on top. And then that's over 1 minus 3 sine 2x. Now the next one is, this will be the last one I do in this lesson. This is a little bit more complicated. Now, one of the things that I have not been doing is using things like substitutions. And with trigonometry, you'll see a lot of the time people do use substitutions just for the sake of keeping it clear and easy. And so for the previous question, for example, some people might have replaced 1 minus 3 sine 2x with a variable like u. And I did not, because I deemed it manageable without it. But in this case, I am going to make a substitution. Now, the substitution I'm going to make is let u be equal to 5x squared minus 1 to the negative 1. Now, some of you, if you didn't, if you were doing it on your own and you're told make a substitution, might have made the whole thing equal to u. And then this expression becomes y is equal to u to the 3. Works out fine, too. I think this way that I'm going to do is a little bit easier, but you can't always tell that at the start. So it's either way would be fine. Either way is better than not using a substitution, period. So when I take the derivative of this, du dx, I get negative 5x squared minus 1 to the negative 2 multiplied by the derivative of the inner, which is 10x. So du dx is equal to negative 10x multiplied by 5x squared minus 1 to the negative 2. Now, I'm not going to deal with that negative exponent yet, because this is just a sort of a working file. As well, I use du dx. U prime is fine as well, of course, because it's your own work and you're just recording it yourself. So we'll see that a lot. But anyways, what we get now is this expression is the cosine of u to the exponent of 3. So it's a lot easier to do the outer differentiation, because dy dx is equal to 3 times cosine of u to the 2 multiplied by the derivative of the inner, which is cos u. Now, actually, this is d du, if you like. Now, the derivative of cos u is negative sine u. And then the derivative of the inner would be du dx, which we conveniently have right above us. So this turns into negative sine u. So negative sine 5x squared minus 1 to the negative 1 multiplied by du dx, which is negative 10x multiplied by 5x squared minus 1 to the negative 2. And then we still have at the front of this expression 3 cosine of u squared. Now I don't have the space to put it there yet, so now I'll rewrite it. So dy du is equal to 3. Now we have 3 times negative 1 times negative 10. It's going to give us positive 30, and there's an x term there as well. And then this is multiplied by the cosine squared of u, which is 5x squared minus 1 to the negative 1. And then we have the sine of 5x squared minus 1 to the negative 1. And then the 10x is taken care of. Now, that 5x squared minus 1 to the negative 2, I'm going to write that on the bottom because it's a negative exponent. Keep in mind that that 5x squared minus 1 is being multiplied by the trig functions. It's not the argument. So we're not taking the derivative of it. So we are free to put it somewhere else. In fact, I would certainly recommend that you do, just so that it's clear and easy to read, because that's usually the problem with these ones. In any case, this is what we get. So it takes a bit of practice to get comfortable with them, but that's a good start. So the next lesson we'll go further and go do some of the extra ones that are on the lesson handout. Thank you for your time.